Hello everyone and welcome to the video 4 of S block elements. And for today we are going to discuss about the alkaline earth metals. Now when we are saying about alkaline earth metals, these are the elements which belong to the group 2 of the S block elements. Okay, so they belong to the group 2 of S block. Okay, now we'll observe what are the different elements that we have under this particular group. Okay, as we start, this particular section or this particular set of element starts with the element, and that is beryllium. Be refers to beryllium. Okay, now beryllium. Next one, what we have is magnesium, followed by calcium, strontium, barium, and finally radium. Okay, these are the particular elements what we have. In order to compare the set of properties of these with the previous set of elements, that was again of the S block, that was group number 1, alkali metals. Okay, so in the alkali metals, what we had was lithium, followed by sodium, potassium, rubidium, cesium, and of course the last one, francium. Radioactive. As this is radioactive, you can consider even radium as to be the radioactive element. Okay, now as we start with this group number 2 of S block elements, okay, we'll start with the first one, and that is with respect to beryllium. Again, beryllium falls under a lot of exceptional cases because of its smaller size. Okay, and again, because of its smaller size, it tends to show the properties equivalent to that of aluminium. Okay, to that of the aluminium, and therefore, what happens is that it shows diagonal relationships. Okay, so it shows us diagonal relationship. Now, as we start our studies with the first property, and that particular property is the electronic configuration. Now, under this particular S block or S orbitals, we know that S orbitals have a capacity to accommodate 2 electrons. Accordingly, the 2 sections were formed in S block, group 1 and group 2. Correct? In group 1, what was happening? The last electron, the differentiating electron, was entering into the S orbital of the valence. Same thing happens here. Okay, but here what happens is we already have 1 electron in the first case, and the last differentiating electron again enters into S orbital, therefore giving rise to the group 2 elements of the S block. Okay, so therefore the electronic configuration over here will become as electronic configuration of the noble gases followed by NS2. So this is important. So, the electronic configuration of alkaline earth metals is electronic configuration of noble gas followed by NS2. Therefore, our S orbital is now completely filled in this particular case. Okay. Now, whenever these particular elements will form compounds, okay, when it reacts and when it forms the compounds, these compounds similar to that of alkali metals are ionic in their nature, and we need to remember this. These are going to be ionic in nature. So this completes our first property, and that was about the electronic configuration. Coming forward with the second property here, and from here we require the help of the entire periodic table. Okay, now in the second property it is going to be the atomic sizes, or we can also call it as ionic radii. Okay, so atomic sizes and ionic radii. Now, please understand, try to recall that as we travel from the left to the right in a periodic table, what happens is the size of an atom goes on decreasing. Okay, now here if we apply the same concept here, that means these set of elements, that is your beryllium, magnesium, calcium, strontium, barium and finally radium. Okay, these particular things have smaller size when we compare to that of our alkali metals. Alkali metals are the largest one in a particular period, right? So therefore, these particular elements will become a little bit smaller in size, and therefore here alkaline earth metals have the sizes smaller than that of corresponding alkali metals with respect to the size. Now question is why? Why are the sizes of alkaline earth metals smaller when we compare to that of corresponding alkali metal? It is all because as we shift from alkalis to the alkaline, okay, here the sizes of this atom shrinks because of the increased nuclear charges. The number of protons are greater, the number of electrons are greater, but the number of shells yet remains same. Correct? So the reason why it is happening, it is because of increased nuclear charge. Due to this particular reason, what we can see is these set will have smaller sizes compared to that of the alkali metals. Now, as we travel down a particular group, that is in the alkaline earth metals, when we travel down a particular group, that is right from beryllium, let's say we take into consideration till barium. As we travel down, the size of atom goes on increasing. That remains as usual for the set of all particular elements in a respective group. Correct? So as we travel down, the atomic size increases with increase in the atomic number. Okay, so this is about the atomic sizes. So, coming forward with the third property of the alkaline earth metals, and the third property over here, as we have, is going to be the ionization enthalpy. Okay, now we are going to study about the ionization enthalpy with respect to the comparison with the alkali metals. Okay, in order to understand this much more in easier manner, let me take into consideration of the two elements. One we will select it from the alkali metals, and the another one we will select it from the alkaline earth metals. Alright, so selecting one, and that is going to be, let's select sodium for our explanation. So as we select with sodium, atomic number is 11, right? And let's select one more element, and that will be from the alkaline earth metals, and we will select over here the corresponding element, and that is going to be magnesium. And as we know, atomic number is 12. Okay, now let's observe the electronic configuration. So 1s2, 2s2, 2p6, 3s1. This is what we have for sodium. 11 electrons should be there, so 2 plus 2, 4, 4 plus 6, 10, 10 plus 1, 11. Correct? Now, coming forward with magnesium, electron configuration, 1s2, 2s2, 2p6, and finally 3s2. Let's take the structures of both of these. Okay, so first one, let's represent sodium. Let's consider this particular white dot as nucleus. Let's say this is our shell number 1, shell number 2, and finally the shell number 3. So, this is sodium over here. Okay, so the number of electrons that we have in sodium, shell number 1, we have 2 electrons. So let's say this is 1, this is the second one, 2 electrons over here. Okay, so 2 electrons. In shell number 2, we have total number of electrons as 8. Okay, so 1, 2, 3, 4, 5, 6, 7, and 8. Final one, as what we have here, is 3s1. Okay. Now, according to the previous character, what we know is the size of the alkaline earth metals are a bit smaller compared to that of alkali metals, corresponding alkali metals. So, let's observe with respect to magnesium now. Now here, let's consider this as the nucleus of magnesium, shell number 1, shell number 2, shell number 3. Let's say this is the third shell. Alright, so we have 2 electrons in the first shell. So first shell, let's represent 1, 2. Okay. In second shell, we have total number of 8 electrons. So let's go with 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so total number of electrons so far now are 10. And of course, we have 1 here and the next one here upon the 3s. So let's say this is our magnesium. Okay, so what exactly is ionization enthalpy here? Is nothing more than the amount of energy required in order to remove the outermost electron from an atom in its gaseous state. Correct? So now, in the case of alkali metal, if it loses one electron, it yet has the completely filled outermost shell. Okay, it will have a completely filled outermost shell if it loses 3s1 electron. Okay, so therefore it will be quite stable in its Na+1 state. Now, here, of course, you require in order to submit or to supply certain amount of energy. But in the case of magnesium, already the size has been shrinked. The size of atom is smaller than that of the alkali metals. So, in these particular alkaline earth metals, because of the shrinking in size, these electrons are held more strongly with the nucleus. The nuclear charge has increased. These electrons are already been pulled more strongly. Okay, so it requires more amount of energy in order to remove electron. So the first case, that is for the first ionization enthalpy. Okay, what will happen here is that the alkaline earth metals, will have higher energy that compared to that of an alkali metal. Okay, this is for the first ionization enthalpy. That means if I subject this particular atom for a greater amount of heat energy, one electron will be removed. Now, if one electron goes, then this one will become as 3s1 and this one will become as 1s2, 2s2, 2p6 for sodium. 3s1 has gone, that means we are removing this particular electron. Okay, so then what will happen is, even if this particular electron has gone, it's quite stable. So therefore alkali metals will require less amount of energy to remove that outermost electron. But now the conditions will change if we go for the second ionization enthalpy. Here the things will start changing, because now this particular magnesium has left only with one electron. If this one electron also goes out, okay, in the second ionization enthalpy, this one will become stable as Mg plus 2 state. That means it can easily lose this electron. Okay, that means amount of energy required in order to remove this electron will be less compared to that of the first one. But that is a reverse condition for this phenomenon. In case of alkali metals, as these are much more stable in their Na plus 1 state if they lose electron. Okay, so now what will happen? It cannot afford to lose any electron from the inner shell, because it will be completely filled till this point. Okay, if it is completely filled, what we know, it is more stable. Okay, so therefore it will not give electron easily. So in the second ionization enthalpy, if we subject this particular thing to heat again, okay, here things will get reversed. That is, second ionization enthalpy for an alkaline earth metal will be less than the corresponding alkali metal, and this is what happens. Okay, so this is the condition. So in the first case, for the ionization enthalpy, what happens? In the first case, alkali metals are going to have lesser amount of energy for the first ionization enthalpy, while for the second ionization enthalpy, it is going to be the alkaline earth metals which have the smaller energy. Alright, so this is all about the ionization enthalpies. So, coming forward with the next property of the alkaline earth metals, and that is going to be the hydration enthalpy. Now, we already know what is an hydration enthalpy from the previous videos, correct? So, hydration enthalpy is nothing more than how much amount of energy is released when one particular atom or an ion is combined with water molecules. Okay, now in this particular case, when we observe the alkaline earth metals, here the size of these particular ions are smaller because they are existing in M plus 2 state. Okay, nuclear charge has increased dramatically in this particular case when we compare to that of the alkali metals. Okay, whereas in the alkali metals, these metals exist in a form of M plus ions. Okay, so therefore what will happen is, smaller the size of an atom or an ion, more is the hydration enthalpy. Quite simple relationship, due to which we can say that these particular alkaline earth metals are more hydrated, or you can also say that they exhibit more hydration enthalpy when we compare to that of the alkali metals. Okay, because of this particular case, most of these particular compounds remain hydrated. They are obtained in an hydrated form. For example, if we take magnesium chloride, okay, this magnesium chloride does not exist just as MgCl2, rather it is in the form of hydrated ones as MgCl2.8H2O. There are 8 water molecules in composition of this compound. Okay, now when we take a look in a particular group, now we have compared about alkali metals and alkaline metals. Okay, now let's observe what will happen in a particular group of 2A only. So in group 2A only, what we have is Ba plus 2 ion, followed by, extremely sorry, it is Be plus 2 ion, okay, followed by Mg plus 2 ion, followed by calcium plus 2 ion, strontium, and finally what we have is the barium plus 2 ion. Right, this is the sequence as what we have. Now in this case, smaller the size of ion, more hydrated it is, or it will show us more hydration enthalpy, and therefore in this entire case it is the beryllium with a plus 2 charge which is more hydrated, followed by magnesium, followed by calcium, followed by strontium, and the least one is going to be the barium over here. Okay, so barium chloride type of salts. Okay, these particular salts are less soluble in water because of the lower hydration enthalpies. Remember this is for your competitive point. Okay, so this is all about the hydration enthalpy. Okay, coming towards the next section of discussion, and that is going to be the physical properties. So, as we have physical properties over here, let us start with the first one, and that is the physical appearances. Okay, so as we see about the appearances, most of these particular metals, these exist in the form of solid with white, silvery type. The color exhibits as a white, silvery type, sometimes white, greyish type. Okay. When we observe its texture, it is quite shiny or lustrous. Okay, so it is quite shiny. When we take a look at its durability, it is quite soft. It is soft, but it is quite hard compared to their corresponding alkali metals. So when we compare to that of the alkali metals, what we understand is these are soft, but it's not that soft as what we have that of the alkali metals. They are quite harder when we compare to that of the alkali metals. Now, because these particular alkaline earth metals have a tendency to lose electrons, they exhibit electropositive nature. Okay, and this electropositive nature, this thing goes on increasing down a particular group. So it increases down a particular group. That means with increase in electropositive nature, the metallic nature also increases down a particular group. Now, when we take a look into its flame test or you subject these particular elements to flame. Let's discuss first about barium. Okay, so barium over here, the barium salts. When we subject these barium salts to flame, it gives us apple green color. So the color is going to be as apple green. Okay, when we observe that of strontium, it gives us crimson red color. Okay, it is going to give us as a crimson red in color. When we observe that of calcium, calcium exhibits brick red color. It is going to show a brick red in color. Okay, now over here, when we take a look into beryllium and magnesium, in this particular case, the atomic size is already small, because of which there is an increased nuclear charge. Due to the increased nuclear charge, the electrons are held much more strongly. They are held much more strongly to the central nucleus. Okay, therefore, the flame is not quite sufficient enough. The flame energy is not quite sufficient enough for the electrons to get excited to the higher orbitals and then get de-excited. Okay, as it does not get excited with the help of the energy from flame, these particular elements usually remain colorless. Okay, so this was with respect to the flame and what happens to their colors. Okay, so moving forward with the next one. Moving further with some important chemical properties. Let us observe how these particular elements of the alkaline earth metals are going to react first with air and oxygen. So, first one is the reactivity with air and oxygen. Okay, so with air and oxygen, what we have here is, first, let's speak with respect to the two elements which are going to show extremely diverse type of reaction. And that is, when we take into look with respect to beryllium and magnesium. Okay, in this case, what will happen is, these metals, when we take these metals for the reaction, okay, and if it reacts with oxygen, it becomes kinetically inert after some time. Now, kinetically inert, in a sense, it is not going to react further. Okay, it is not going to react because when we have this particular metal, whether it is magnesium or whether it is beryllium, what is happening here is, as it starts reacting with oxygen, at the initial stage itself, it will form a film of oxide on the top. Okay, it will form a film of oxide on the top, resulting in which it becomes kinetically inert. It will not react any further with oxygen. Okay, so it is going to form a film of oxide layer on the top. But if we take this particular beryllium or magnesium, let's break it down in its powder form. Okay, as when we have it as in a powder form, whether it is beryllium or whether it is magnesium, they react brilliantly with oxygen. Okay, they react brilliantly with air, vigorously, in order to form beryllium oxide and beryllium nitride. Okay. So is the case when we take a look with respect to magnesium. So magnesium forms magnesium oxide as well as magnesium nitride. These are what are formed when we take beryllium and magnesium in their powdered form, powdered state. Okay. Now, when we take a look into the different elements which are remaining now, such as of course calcium, strontium, barium, these things are readily attacked by air. Okay, they readily are reacting with air in order to form oxides and different nitrides. Nitrides, the same type of chemical composition. Okay, now when we take these and as we react these ones with water in its cold state, these elements end up giving us hydroxides. So, in competitive exam, they will ask you one particular question on this. Why does not beryllium and magnesium react readily with oxygen? Okay, because it is kinetically inert due to the formation of a thin layer of oxide on the top. Okay, so this is for the reactivity with air and oxygen. Moving further, what we have now is the reactivity with halogens. So as we take a look into the reactivity with halogens, these particular alkaline metals, let's say represented by react with halogens at elevated temperatures. Okay, at higher temperatures, in order to form metal halides. But as these particular metals are existing in M+2 state, it combines with two halogens, and therefore this one will be the molecular formula. Okay, so let's check one example over here. Example: magnesium reacts with chlorine at a higher temperature in order to form magnesium chloride. Okay, now moving further with respect to the reactions with hydrogens. Now remember, in reactions with hydrogen, it is except the beryllium, all other alkaline earth metals tend to react with hydrogen again at higher temperature, at elevated temperatures, in order to form metal hydrides. Okay, so therefore, if we are going to take over here metal, except for beryllium, these particular things will react with hydrogen in order to form MX2. Right? MH2 metal hydrides. Now, as far as beryllium is concerned, how do we construct or how do we do synthesize beryllium hydrides? It is by taking BeCl2, beryllium chloride, reacting this beryllium chloride with lithium aluminum hydride. Okay, so as we take with this reaction, beryllium reacts with hydrogen in order to form BeH2 plus what remains with us is 4 chlorines. 4 chlorines moles, out of which one will react with lithium in order to form lithium chloride. Remaining are three will combine with aluminium in order to form AlCl3. So this is how we do synthesize beryllium hydride. Remember this set of reaction. Now, when we look at its reactivity with acids. Now, acids, what acids are we speaking here? The acids such as hydrogen halides, haloic acids. As metals will react with halogen acids, these of course will form MX2, same type, correct? Metal halides. Along with this, there is a liberation of hydrogen. Okay, so now when we observe this entire thing, of course it's not balanced. In order to balance it, let's take here 2. So 2 halogens, 2 halogens, 2 hydrogens, 2 hydrogens. Quite simple as that. Let's check one example over here, taking into consideration of calcium. Let's say calcium reacts with HCl. Okay, in order to give us CaCl2 plus hydrogen will be eliminated, and in order to balance this, let us take over here as 2. So this is all about reaction with the acids. Let's observe the next set of reactions. So let's observe the next property, which is the reducing nature. So, the reducing nature of alkaline earth metals. Now, one thing that we have to understand is here we are speaking with respect to donation of electrons, how better a substance gives electron. Okay, now let's say this is a substance, and if the substance provides, donates electron, then this substance is acting as a reducing agent. While a substance which is going to accept this particular electron, it is accepting that electron, it is undergoing reduction. Okay, so this substance over here undergoes reduction by accepting that electron. Okay, in short, this substance is taking electron from this, that means this is going to oxidize this substance. It is this particular phenomenon. Gives electron, undergoes self-oxidation. Okay, but it is reducing the another one. It's like this. Now, how better a substance is going to give electron, that is where it acts as a reducing agent. Okay, so when we compare the alkaline earth metals with respect to its alkali metals, as alkaline earth metals are already smaller in size, they cannot easily donate electron. Okay, as it cannot easily donate electron, their reducing nature is quite less when we compare to that of the alkali metals. Okay, so therefore, alkaline earth metals are less reducing in their nature when we compare to that of alkali metals, corresponding alkali metals. So this is with respect to the reducing nature. Okay, now when we speak about beryllium, as beryllium exists in the form of +2 state of its ion, because of its very exceptionally small size. Because of the smaller size and higher hydration enthalpy. Okay, and higher hydration enthalpy. This beryllium is going to be acting as least reducing agent. It acts as the least reducing agent. Okay, so so this was about the reducing nature of alkaline earth metals. Let's observe one last thing, one last property, and that is how do these alkaline earth metals will react when we drop them in liquid ammonia. So, next one is the reactivity with liquid ammonia. So, when we take an alkaline earth metal, just like alkali metals, when we drop them in ammonia, it develops dark or deep bluish black solution. Okay, so when we have an alkaline earth metal, when we subject this one in the liquid ammonia, it develops deep bluish black color. Okay, and when we observe its chemical reaction, let's say we have this metal which represents an alkaline earth metal. Okay, and when we subject this thing with X plus Y moles of liquid ammonia, okay, what will happen is we get here NH3 X plus 2 because metal of alkaline earth metal exists in plus 2 state. So we are getting here as a plus 2. Okay, plus we have electron, okay, in bracket NH3 Y times minus. Now here we will get as 2 in order to balance. Plus 2, this is minus 1. So 2 into minus 1 will become as minus 2. So minus 2 and plus 2 will be compromised. Alright, so charges are nullified in that case. So this is how the reaction occurs with respect to the alkaline earth metals in liquid ammonia. So to take care, we'll meet you in the next video.